the Chinese and the Mongols had a war. It happened around 1232, and the Chinese army repelled the Mongol army using this kind of arrows, which were having this bamboo stick with gunpowder, which was making it travel. So I think that may be the first use of missiles to in the warfare. We have the record of sending 104 satellites in a single rocket. Is a world record, beating the Russians, which were around 40. Actually, we use satellite mirrors, which actually does the imaging, and the camera is actually looking at the mirror. Mirror looks at the Earth's surface. If the mirror distorts, is a problem. Your forest cover is going to change. Image quality is gone. You cannot. Now satellites are there which can read your number plate of your car when you're driving. So the accuracy depends on the surface finish. So I just scribbled something, noted down. We'll try to tell about the rockets because that is my livelihood. I work in that area. The rockets, they say it started long back around so many stages it has gone through. They say in the Greek hero of Alexandria, he did the most elementary thing. What he took is that he took a sphere, and that was some steam was fed into that, and in that sphere he put some two L-shaped outlets. So when steam went in and came out, and they were opposite direction, so it started rotating. If you look, that is the first experiment you can say. When the steam, when it came out, the object moved, which is the basic principle of a rocketry per se. After that, so many things happened, and they say around first century AD, Chinese, they started doing the work on the gunpowder. So what they used to do is that they will fill the gunpowder in bamboo, close the end, and throw in the some kind of fire. So it will explode. So it will be like mostly celebratory purposes. But somewhere they say, we don't know, that some of them did not explode and they moved because one end got loosened and the your explosive came out through that. So when they saw, probably they realized, so this bamboo strip can actually travel. It need not explode. So they started tying these bamboo particles on the arrows and fill the gunpowder. So gunpowder will come out and the arrow will travel farther distances rather than simply throwing. And other the work what arrow does, it will do. But if you look, that is kind of a rocket then. The bamboo, the gunpowder which is coming out of the bamboo and taking the arrow forward is like a rocket. Then, but if you look at that one, they say that it is some charcoal, sulfur, saltpeter, they filled it in. Then something happened when a lot of wars were there. The Chinese and the Mongols had a war. It happened around 1232, and the Chinese army repelled the Mongol army using this kind of arrows, which were having this bamboo stick with gunpowder, which was making it travel. So I think that may be the first use of missiles to in the warfare. Then a lot of work happened in 13th to 15th century. This idea went from China to maybe Arabs to Europe, and they started using it. Then there was interesting thing. Some French one person was there, Jean Froissart. What he did is that he started using this tubes, with much more this arrow when it is traveling. If it can travel through the tube first and then come out, it gives much more better accuracy. So that may be the guided system which was developed elementary. Then when Mr. John Fontana, he came out with an interesting idea. What he did is that he took a small, like a tortoise kind of thing, filled with this gunpowder, and it used to travel on the surface, and it goes and hits the ship, and ships will catch fire. So between the wars, which was generally Europe will fight France, and these people will fight on sea more often. So these were used like a torpedoes, surface traveling tortoises, which were having filled with this. Then in Germany, a lot of things happened. They started inventing the stage rockets. Means first is going to be same type of things only, but first stage is going to be thicker. The next stages are going to be thinner and thinner, and then one will come out. Then second will catch fire. So this is like a stage. Now whatever rockets we are making, they are also stage. First stage solid, second is stage liquid, third stage is cryo. But that started long back, 15th century back. And then I'll just tell that Chinese, there was a person, this is a legend only, it is not real, we don't have a proof. This person name was Wang Hu, it was some kind of official. He came with very nice idea. He had a chair, and that chair he tied with two big kites, and each kite ends, he put some small rockets, the same bamboo filled with gunpowder, and 47 numbers is what the story says, and some 47 attendants. So they rushed, and he said, when I sit on this, you fire it. So rockets will fire, I'll go up. So it happened, it seems. But after the fire happened, nobody could find the chair and that Wang Hu. It blown into pieces. So it was not very easy. Then the American Robert Goddard, he started doing lot of experiment. He is said to be one of the pioneers with solid rockets, and also he was the first person to experiment with the liquid. So he used gasoline and LOX. LOX is liquid oxygen in the rocket. So that may be the first liquid rocket. The flight was very less. It was hardly 2.5-second flight with hardly the altitude of 12.5 meters is what it went. But that is the first liquid engine, we can call it liquid rocket, which went. And then Germans started making V2 rockets, which was like a missiles, liquid propelled, and they started throwing it on the England, and it was destroying like anything. And what they say is that then why they lost? Probably they used it quite late in the World War II, 1937 and all. Had they started earlier, the war would have resulted in differently. Now, after this V2 rockets, which are so successful, the German got defeated. This technology was stolen from Allied forces, that is, Americans, not stolen, taken away, the war booty. And to some extent by Russian also. There was a joke, the famous comedian said that why the Russian rockets are going, why our rockets are not going. I think sir knows that. So he joked, their Germans are better than our Germans. So basically German only are making the rockets. 1957, we all know, Russia launched the Sputnik. And within a month, they launched the second one, in which they put the dog named Laika. Laika survived for 7 days. Oxygen went out, then they died. Then Americans also started. Explorer 1 came 1958. And it progressed. We also started having rockets, and so many rockets. PSLV in 2017, when we sent, it had 104 satellites. Yesterday, somebody was saying 36 satellites. It's not true. We have the record of sending 104 satellites in a single rocket. It's a world record, beating the Russians, which were around 40. And this Sunday, we are also going to send GSLV Mark III, which is going to be our workhorse. Probably other rockets will slowly die away because it has a good capability. And what we are going to launch is 36 satellites from OneWeb. This is also interesting story. I think I should better tell it. OneWeb wanted to send, this is a British company, they want to have a constellation of so many satellites, around 648 satellites they want to have. And they have already launched 582 satellites using Soyuz primarily, then Falcon 9, US. The contract was not over, and the Russian war, that Ukraine war has started. So Ukraine war started, though there was obligation, we should not do things with Russia. So they approached us, can you launch? Which we happily agreed. And last mission, Mark II, was with OneWeb, 36 satellites were launched successfully. It is said to be one of the biggest success. Maybe somebody will tell you the story how it was launched. I'm not going to tell right now. The design of the flight was wonderful. Then 36 more is going this Sunday. Now, coming to the rocketry and coming back to the same topic, the materials in the rocketry. And before that, I wanted to tell one story I was telling. Not only Sky, we are trying to help even the, for deep sea exploration. Deep sea, there is a mission for making a submersible, deep sea submersible, which can go to 6,000 meters down. But the pressure, when you go deep in the sea, is very high pressure. You can't survive. Any vessel will simply crumble. Nothing will be there. So it needs a titanium, which is lighter weight and high strength. And we want 3 people to be sitting in that. So it's going to be a big sphere of 2.1 mm diameter, 1 meter diameter. And with the National Institute of Ocean Technology, this ISRO is helping, because we have rich experience in making titanium alloy gas bottles. So with the help of many industries, Midhani and all, this is going on. So we always support, Ms. ISRO is always taking the other activities with the other organizations also. Now, challenges in the materials for space applications is multifold. It's not single, because we maybe the people who have materials for 20 Kelvin, that is liquid hydrogen. At the same time, when the thrust chamber burns, the temperature goes to 3000 degrees. So we deal with the materials with very low temperature to very high temperature. We deal with the environments which are highly corrosive, hydrogen, to the highly erosive, that is your nozzles where the things come out, oxidative, satellite thrusters, very low thrust. So all type of materials, you name it, aluminum alloys, we is like a workhorse, everything we make mostly with aluminum alloys, copper alloys, for thrust chamber. I'm not giving a full details, but each topic is a big topic to discuss. Copper alloys we use in thrust chamber where we need high thermal conductivity. High thermal conductivity, pure copper will give, but we have to compromise to gain the strength. It always remains a open challenge to build this system. Like we need a copper alloy which gives us the thermal conductivity as close to the pure copper, at the same time gives the strength. Maybe Dr. Vinod was talking that after this discussion we'll try to pick up some ideas where ITs can work. So this is one. You can have a copper alloy which gives high thermal conductivity, doesn't compromise on the pure copper conductivity, but strength is also high, and strength is also at high temperature. We deal with magnesium alloys, titanium alloys, all alpha alloy, alpha beta alloy. Like, when you go to 20 Kelvin, everything becomes brittle. So we need a titanium alloy which is still ductile at very low temperature. The titanium, why it sank. It went into ductile to brittle transformation during that Atlantic, and due to low temperature, it became brittle and cracked. Now, steels, nickel alloys. Nickel alloys are high temperature alloys. Any application which demands application 600 and above, you need to go for super alloys. So we have that cobalt based super alloys, niobium based alloy. Niobium based, like we call it columbium, C103. It's a columbium hafnium alloy which is used in satellite thrusters. Unfortunately, everything is imported. All the niobium is coming from outside. So you need a material. We'll say 2047 we have to move somewhere. We have read literature. Now NASA is working on rhenium based thrusters. Now rhenium is going to be much more costlier even than columbium. For us, small satellite thrusters, why can't we come out with some other material which can work at, let's say, 1400 degrees centigrade, should not oxidize, because when the burning takes place there is oxygen. So even in columbium alloys, that niobium alloys, we give a silicide coating which protects it from the oxidation. So we need a material. People have come up with the idea that carbon SiC or SiC composite can be used for thrusters, but fabrication of such a small thing with the nozzle diameter of 0.2 mm or 1 mm range is not going to be easy. So fabrication challenges also. So this is a topic. Can you come with the material which is lightweight? Space also always wants materials which is having low density, because we are going to take it up, more weight, more money we are going to lose basically. More propellant, more structural mass. This is going to be real difficult. This is a topic. We also work on Maharajing. I have not talked. Maharajing steel is like, all motor cases are made. Somebody was telling us last day that somebody was trying to smuggle Maharajing steel where we are making in Midhani. So we use a lot of Maharajing steel. Then ceramics is not only metal system. We work on ceramics. Silk mirror. There were a lot of talks on the mirrors. Actually, we use satellite mirrors, which actually does the imaging. And the camera is actually looking at the mirror. Mirror looks at the Earth's surface. If the mirror distorts, is a problem. Your forest cover is going to change. Image quality is gone. You cannot, now satellites are there which can read your number plate of your car when you're driving. So the accuracy depends on the surface finish of the material which is used for mirrors. And when the satellite rotates, the temperature changes from 150 degrees to plus 50 degrees. You cannot have any coefficient of thermal expansion. Kannadi mirror is good. Your mirrors, we have candidate material. Silicon carbide based mirrors are being used. Zero door, which is a lithium aluminosilicate things, which is interesting heat treatment study. There is a alpha, which is positive and negative. The crystalline phase is having positive, amorphous phase is having negative. You do the suitable heat treatment, you can nullify it. The CTE of that zero door material is zero, just by doing suitable heat treatments. Beryllium mirrors are used, but beryllium, is highly carcinogenic. You cannot handle. In Vasi, DAE has a plant where they process beryllium. There is a hot press. I have seen that. So the entire room is like a partial pressure, so that any beryllium which comes out during processing goes away. But it's going to be risky. It's not going to. The beryllium used in the mirror is coming down. I remembered, so I just put it. Carbon-carbon composite is a ceramic we are using extensively, but it's a very good material, 2000 degrees, low density, but you cannot use any oxygen is there, carbon will go away. It will simply get oxidized. So you have to protect it from the silicon carbide generally give. So protective coating. Now protective coating, how protective it is, we have to see, because silicon carbide will shrink, it creates crack, gone. Alumina, barium titanate, piezoelectric, so many ceramic materials, CSIC. Even now we are working on the plasma thrusters. Very interesting topic, because in satellite we don't need very high thrust. We need minimum mass to produce the maximum thrust. So plasma, we carry the xenon. Xenon is converted into ion, and ion is propelled through the electric and magnetic forces. And when it comes out with a high velocity, it gives the thrust. As a very high ISP, we call it ISP, specific impulse. That is how much thrust you generate per unit mass. So that is as good as 4,000, whereas in the other normal cryo engine also gives around 430, 450 like that. So very high thrust. There we use boron nitrate silica. We have started making in India. Earlier we were having import. Now silica tiles, thermal protection systems. Protection means like you are aware of Columbia disaster. The silica tile broke off, and what happened. So we have made, and in SRE2 we approved. Now joining technologies. Because we use so many materials and we cannot have every place nut and bolt and screw, we have huge amount of joining technologies, conventional, like TIG welding, EB welding, brazings, more than 200 types of brazings are there. Dissimilar materials joining, similar material joining in the semi-cryo engine. Diffusion bonding, we do a lot of work on that. Friction stir welding, friction welding, all the aluminum alloys to 219, even the next generation aluminum lithium 2195, we want to go for friction stir. There is a difference between friction stir and friction. I think our young colleagues may know. There is a difference. Explosive bonding also we have used. Then coatings, we use lot of coatings, not only corrosion protection, it is protection for so many things, like nickel coating is thing, you have abrasion resistance, lubricant. When you have a nut and bolt, we want to give a coating which makes the friction less. MOS2 based coatings are being used. Then metal ceramic coating is interesting topic. I work on that. Just I'll tell something about that. The semi-cryo engine uses oxygen recycle, and that condition metal can get ignited. So protect from that, we use metal ceramic coating. Then silicon carbide coating for oxidation, silcide coating again for thrusters, high emissivity coating. When we made the silica tiles, when the radiation comes, if it goes back, the heat pickup will be less. So for that, high emissivity coating, that is Syria based, was also developed and proven. Then thermal barrier coatings, zirconia, yttria stabilized, calcia stabilized, that kind of things are also used. And so many special materials, magnetic materials, energy materials I have not talked, batteries. So much scope is there all over the world. I think everybody is trying to work on energy materials, because in future, most of the vehicles will run on the batteries, and you need batteries, good quality batteries, and you cannot simply be dependent on lithium alone. You have to develop. If the battery cost come down, I think the electric vehicles will take upper stage. Till that time, still fossil fuel will run. Magnetic materials we want to develop, but all the magnetic materials use rare earth. And rare earth is only coming from one country. If that country backs out, we know what will happen. So So we have to work on that. We have to develop magnets which are rare earth free, so that we get self-reliance and low expansion materials. Many satellite application we work on the materials which doesn't expand, but nature, materials, metal, you use a very high CT, ceramic means so much brittle you cannot use. So there is a lot of topic and we work powder metallurgy. With that, I'll conclude.